Okay, let's try to solve some antiderivative problems. Remember, this symbol here to the left and to the right of it means is like a parenthesis. It means to antiderive what comes in between. So in this case, we're trying to antiderive 15 cosine x dx. And the key here is to actually imagine the 15 is not there for right now, and antiderive cosine and realize, oh, that's sine of x. Then remember that 15 was actually there, and just multiply your answer by 15. And then remember to go to the ocean plus c. So 15 sine x plus c. So when there's a number in front, you can kind of ignore it, antiderive the rest, and then just put it in at the end. The antiderivative of secant squared of 4x, remember, that must have started with tangent of something. In this case, it's the tangent of 4x. I'll leave the inside function alone. Then I have to divide by the derivative of the inside, so times 1/4 plus c. Next problem is an anti-chain rule problem where you have to antiderive the outside with respect to the in. So this would be 1/4, leave the inside alone, to the 4th power. And then you have to divide by the derivative of the inside, which is times 1/7, and don't forget to go to the ocean, so plus c. So 1/4 the quantity, 7x plus 3 to the 4th power, times 1/7 plus c. Okay, here's some other problems. X squared to the 5th, realize we could try to antiderive this with the anti-chain rule, but remember, dividing by the derivative of the inside requires us to divide, in this case, by an equation. Dividing by 2x is a big no-no unless it cancels, okay? So what I'm going to do here is I'm actually going to simplify this equation and realize this is the same as x to the 10th dx, and then antiderive that using the anti-power rule. 1/11 x to the 11th plus c. Next problem is another one where the derivative of the inside is actually an equation. So I'm going to look at here and realize, let's rewrite this as sine 2x, the whole thing to the 5th power, times cosine 2x dx. And then it's really easy to see my outside function is to the 5th power. So I'm going to antiderive that by anti-powering it, 1/6 sine of 2x, leave the inside alone, to the 6th power, divided by the derivative of the inside. The derivative of the inside here is cosine 2x times 2. And the cosine 2x actually cancels, but the dividing by 2 doesn't. So I got to throw in a 1/2 here, and then plus c. So again, I have to follow the anti-chain rule explicitly. Antiderive the outside with respect to the in, divided by the derivative of the in, and then the plus c. Next one is just to see if we can remind ourselves how to implicitly derive, where this requires the chain rule. If you notice, I have u and v, different variables, but I'm going to use the chain rule here. So the derivative of the first is 6x, leave the second one alone, plus, now leave the first one alone, and derivative of the second is 3y squared times y prime equals 0. And then to solve for y prime, I would subtract 6xy cubed from both sides, and then divide by the number in front, which in this case is 3x squared times 3y squared. And if I simplify that a little bit, I'll realize I'll get negative 2y over 3x. So check and see how I got that. Okay, so we learned today that the mean value theorem means derivative equals slope. So a classic problem on the AP exam would be to say, take the equation f of x equals 2x cubed on the interval from 3 to 5 and find the value that satisfies the mean value theorem. So in other words, find c. Well, remember, the derivative equals the slope. So it's going to be the derivative of this is 6x squared equals, I'm going to plug 5 into this equation, that's y2, minus, I'm going to plug 3 into this equation, over the difference in x's. So in this case, this becomes 196 over 2, which is 98. So if I solve this equation, 6x squared equals 98, I get x squared equals 16.6, I'm sorry, 16.3 repeating. And then if I square root both sides, I'll get x equals the square root of, which gives you x equals 4.04, which if you notice is in between the two values 3 and 5. So this is a classic way that they'll ask the mean value theorem on the AP exam. Okay, this leads into the final formula in calculus, or another theorem. It's called the fundamental theorem of calculus, which gets its own abbreviation, FTC, which is accepted on the AP exam. And this formula allows you to find the exact area under a curve without estimating, without using, early on we used trapezoids, without counting squares, or without using this Riemann sums, or using rectangles. And basically it says that if you want to find, by the way, this is a symbol that means a definite integral. You see it looks very similar to an indefinite integral. The difference is I have the two bounds. When I see the two numbers there, I'm asking for the area under the curve. So if I want to find the exact area under the curve from a to b of any function, I find g of b minus g of a, which g is the antiderivative of the function. So in other words, I antiderive the function, plug in the two bounds, and subtract them, and this gives me the exact area under the curve. So for example, if I wanted to find the area under the curve from 1 to 4 of x squared dx, without using trapezoids or without using the Riemann sums, I can actually find this by antideriving this function, which would be 1/3 x cubed plus c, and then plugging in both 4 and 1, and I use this symbol to represent that I'm going to plug in 4 and 1, means evaluated from 1 to 4, and then we're going to subtract. So I'm going to plug 4 into that and get 1/3 times 4 cubed plus c minus, I'm going to put 1 in there, 1/3 times 1 cubed plus c, and then simplify that equation. First thing I note is the c minus c does cancel. 4 cubed is 64 over 3, minus 1 cubed times 1/3 is 1/3. Well, 64 thirds minus 1/3 is 63 thirds, which turns out to be 21. And this is the exact area under the curve of x squared from 1 to 4. And this is how you evaluate definite integrals, coming up with an exact answer. A lot easier than using Riemann sums or trapezoids or any of those other methods. So this is the fundamental theorem of calculus that we will be using a lot for the rest of this year.